Assalamualaikum warahmatullahi taala wabarakatuh, and a very good day for all examiners and panels. Kindly today I would like to present about MEC 601, the final year project 1. Before that, I would like to introduce myself first. My name is Nur Aiman bin Amran, and my supervisor's name is Dr. Muhammad Nur Hisham bin Abdul Rani, and my co-supervisor's name is Professor Madya IR Dr. Muhammad Azmi bin Yusof. And my final year project name is Investigation of the Mode Expansion of a Car Front End Module. So let we start it. Before we go through further, this slide presentation cover about 5 main topics and are following with a subtopic, starting with our project summary, second, introduction, and third is a methodology, fourth, expected result, and lastly, references. So we go to chapter 1, which is a project summary. For this project is performing experimental model analysis on a geometrically complex structure such as a car front end module. And then the difficulties arise because the responses on the certain degree of freedom cannot be measured due to limitation for placing accelerometer with accurate orientation. Then, the natural frequency and work shape of the car front-end module will be measured using experimental model analysis, EMA. Lastly, the EMA will be performed on a free boundary condition, and SEREP expansion method will be performed to obtain the unmeasured degree of freedom of the car front-end module. Uh, then the outcome from this work is expected to provide useful guide for obtaining the unmeasured degree of freedom of a geometrically complex structure. Next, we cover chapter 2, which is introduction. Generally, a vehicle, especially a car, whose component consists of various structure is an important element in involvement with a vibration phenomena. Undoubtedly, in almost all actual practical situation, structure with complex geometry will experience difficulties and inconsistencies in comparison of measurement between FE, which finite element, and the experimental model testing. Usually, the incompatibility appear due to two different things. The first one is that only a certain degree of freedom can be measured. Second, not all mood shape can be measured. The difficulty also arise because of limitation for placing accelerometer with accurate orientation. Besides, the data acquisition equipment also make the frequency range to be measured have a limit. In general, the finite element model is widely used and conventional. This method could be very large to several thousand degree of freedom can be measured in some cases. Thus, the difficulties that arise can be overcome and solved by using mode expansion method, MEM. In performing the expansion process, there are 4 main techniques used, but in this study only focuses on use the setup expansion implemented on 3 different EMA of the car front end module, and then the accuracy of the expanded mode shape is then evaluate and quantify using model assurance calibration MEC analysis. Okay, we still in chapter 2, which is I would like to talk about literature review. In this literature review, bolted 2 different elements, which are finite element model and analysis, and also the mode expansion and model assurance calibration. From the previous studies and a few journal and research paper that I got from website and other resources, it's claimed and explained that the finite element method is basically the most frequently and effectively used to model the complex structure like as bridge, building, dam, containment vessel, and so on. And then The other research paper in expansion of experimental mode shape from operational model analysis and virtual sensing for fatigue analysis using the mode expansion method. They explain that in order to produce the transformation between master and slave coordinate, Serep expansion use theoretical eigenvector. It is very precisely related to the expanded mode shape. So next, I would like to explain about problem statement for this project. To be specific, front-end module of a car will definitely vibrate when a resonance occur. It causes a structure to suffer a bad damage. And then the modal parameter such as natural frequencies and mood shapes of the car front-end module is essential information for the dynamic analysis on the structure. And lastly, degree of freedom are difficult to obtain because of complex geometrically structure due to limitation to placing accelerometer with accurate orientation. So next is objective, scope of work and limitation for this project. They have three main objectives, which are to develop the finite element model FEM of a car front-end module. Second, to determine mode expansion method using three different of MR model of the car front-end module. And lastly is to evaluate the accuracy of the expanded model of the car front-end module. And for the scope of work and limitation, first is the frequency of interest is between 0 to 500 Hz. Second, certain degree of freedom will be investigated by using EMA. Third, no boundary condition are including for the modeling. Fourth, the mode will be solved using normal mode analysis solution. Five, for the test, the structure will be tested under free boundary condition. And the lastly is the structure will be merely tested using impact testing. Okay, now we jump to chapter 3, which is methodology. Before that, I would like to show you flowchart of the project. It started with developing the finite element model of a car front-end module. Next, developing three different of MR model, and then performing Serep method using the three MR model. Then after that, performing make analysis, and lastly, evaluating the accuracy of the expanded model of a car front-end module. Okay, next, the description of the test structure. The proposed approach will be implemented on the front-end module of a car. As a case study, this structure is used because its configuration is considered to be the main and important role in the vibration level of car. There are 9 components located on the test module installed using 76 welded joint of resistance, shows in figure. The component range in thickness from 1 mm or millimeter to 1.4 millimeter, and all the components are made of galvanized steel. Sorry. And then the component also has an overall weight of 2.45 kg and its length is 960 millimeter. Okay, then next, develop the finite element analysis using MEC601. In implementing the finite element model in CAA software, which is MEC601, 2D shell elements are used in the expansion of FE model as shown in figure. Since the geometry of the test module is so complex, several variations of element size are used in the range of 5 millimeters to 8 millimeters. Therefore, in the creation of the FE model of the test module, a total of 6,010 nodes and 5,530 elements were developed. And it's consisted with young modulus of 210,000 megapascal, portion ratio of 0.3, and density is 7.850 kg per meter cube. Okay, now we go to experimental model analysis, the car front end module. The experimental mode analysis begin by rigging all the equipment as shown in figure below. The test module is suspended using two soft springs to simulate the configuration independently, while a 21.65 meter volts per Newton shock hammer with 3 improper 10 millivolt acceleration is used for measurement. The test module is also connected to the SCADA measurement system (LMS) to obtain the dynamic data after the test module is tapped at all points that have been determined to obtain the full EMA model. Okay, the experiment was also set with a frequency resolution value equal to 0.5 Hz and a frequency bandwidth in the range between 0 Hz to 512 Hz. In the success of this work, experimental mode analysis (EMA) is used in measuring the natural frequency and mood shape of the test module. In addition, three types of measurement configuration are also designed and conducted to model different elements. Okay, next subtopic in methodology is development of mode expansion method in EMA. As you can see in slide presentation, shows the type of measurement configuration of the car front end module. First is full EMA configuration. Second is middle only measurement configuration. Third, both side only measurement configuration. And lastly, 1D line measurement configuration. There is only one technique applied in the expansion mode method for the expansion process for this work, namely as serif expansion. Serif expansion can determine the unmeasured and difficult mood shape and natural frequency. The serif expansion method is applied according to the equation below. Okay, so now we go through chapter 4, which is expected result. In expected result also have a preliminary outcome. But first, I would like to show you the expected result. The first is the natural frequency and mood shape of the front end car module can be successfully calculated using normal mode analysis. Second, using different EMA model will result different expanded mood shape. And lastly, the expanded model is expected to be accurate with the EMA result. As you can see the figure below, it shows the FRF reference point of the car front end module that has been tested. There were 52 unidentifiable measurement points, while the 52-point response was measured by two roving accelerometers. The test structure was completely excited 10 times to obtain the good and reliable data result. All responses were analyzed using the LMS test lab, while a least square method curve fitting procedure was used to obtain the frequency response function. Continue the preliminary outcome. In determining the quality of FRF measured from the FRF excitation point, an analysis approach is performed in observing the result of coherence function. The quality can be applied and accepted if the coherent value approaches 1.0. The average result of 10 times excitation of the reference point coherent shown in figure, and it shows a good coherent value when approaching 1.0. Then second figure is the total of FRF of 52 measurement point presented from 8 mode. defined within the frequency range of interest. Okay, next topic is cover for comparison of natural frequency between initial FE and full EMA. The diagonal value of MEC, which are close to 100%, usually express the similarities between the FE and the shape of the measured mode. Six modes were determined from the finite element model and EMA in this work. As you can see, there was a lack of correlation between the initial FE and EMA in terms of natural frequencies, particularly for the fourth and sixth modes. And in comparison, a high MEC value in mood shape was measured with 4.36% error. The mode 6 is the largest contributor to the 11% of total error. The fourth mode also recorded the lowest 89% MEC value. Okay, last but not least, the comparison of mood shape between initial FE in column and full EMA in row. Uh, in the table shows the assessment of similarity of mood shape between the finite element model and EMA was analyzed using model assurance calculation max. And the table shows the diagonal MEC value for the mood shape. It is clearly seen that with 89 and 89.2% respectively, low MEC value were found in the fourth and sixth modes. However, in this study, only interested in the first six natural frequency and mood shape obtained because it is considered sufficient for the final year project level. Okay, that's it from me. To all the examiners and panel, thank you so much for watching my final year project presentation. Thank you for your time and thank you for your cooperation. Thank you.